Hello there, and welcome to the Sleepy Space Channel. Every planet in the Sun's family spins more or less upright, except one. Uranus lies on its side, tipped so far that it rolls rather than spins as it circles the Sun, with one pole turned toward the light and the other into the dark. Something laid this world down near the beginning of everything, and no one is entirely certain what. The favored answer is a great collision, a glancing blow from a body several times the mass of the Earth. But quieter explanations linger too, a lost moon, or a slow gravitational pull across an age. Tonight we follow the whole unresolved question, and everything the tilt has done to this distant, sideways world. If you find these quiet explorations worth your time, a like or a subscribe helps the channel reach others who would enjoy them too. Thank you for being here. But for the next couple of hours, none of this is something you need to carry. There is nothing here to solve and nowhere you need to be. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade gently away behind you. Let's begin. Something happened to Uranus long ago that happened to no other planet in the Sun's family. Every world we know spins more or less upright as it circles the Sun, standing like a top on a table, leaning only a little from straight up. Uranus does not. It lies on its side. Its axis, the invisible line running from one pole to the other, has been tipped almost a full right angle, until it rests nearly flat within the plane of its orbit. And so the planet does not spin as it travels. It rolls. The strangeness of this is easy to overlook when it is written as a number, so it is worth sitting with for a moment. Picture the other planets as spinning tops, each one turning about an axis that points up and down while it glides around the Sun. Now picture Uranus among them, its own axis turned on its side, so that one pole points roughly toward the Sun and the other points away, and the whole world turns like a ball rolling along a track. That is the single most unusual thing about this planet, and it is the quiet mystery this long night will slowly unfold. The tilt is not small, and it is not gentle. Earth leans by about 23.5 degrees, and that modest lean is enough to give our world its seasons, its long summer days and short winter ones. Mars leans by a similar amount. Saturn and Neptune lean a little more, but still hold themselves broadly upright. Jupiter barely leans at all. Against this quiet company of upright worlds, Uranus is tipped by about 98 degrees, which is just past a right angle, until its axis lies almost level with its own orbit. Because that tilt has carried the planet a little past flat, Uranus turns, by the careful bookkeeping astronomers use, in the opposite sense to most of its neighbors. It rotates slowly backward, in the same broad category as Venus, though for an entirely unrelated reason. This detail matters less than the plain fact beneath it. Whatever the precise angle, and whichever way the numbers are counted, Uranus is the one major planet in the Sun's family that lies down rather than stands. The word that first comes to mind for such a world is often a dramatic one, and the popular telling of this planet tends to reach for it. Yet there is nothing violent about Uranus now. The violence, if there was violence, is long finished. What remains is a calm, cold, pale, blue-green world, turning quietly on its side at the far edge of the Sun's family, keeping to itself the story of how it came to lie down. The tilt is not a wound the planet is still suffering. It is a settled fact, an old accident carried gracefully for a length of time the mind can barely hold. Nearly everything else that is strange about Uranus can be traced back to this one fact. The extreme length of its seasons follows from the tilt. The odd arrangement of its moons and rings follows from the tilt. Even the long argument about the heat missing from its interior is bound up with the same history. To understand why Uranus lies on its side is, in a real sense, to understand the whole planet, because so much of what makes it unlike its neighbors flows from that single tipped axis. Uranus is one of the two worlds astronomers call the ice giants, the smaller and more distant pair of the four great outer planets. It is far larger than Earth, holding roughly 14.5 times our world's mass, and wide enough that dozens of Earths could fit within it. Yet it is dwarfed in turn by Jupiter and Saturn, the true gas giants closer in. Uranus and its near-twin Neptune are made in large part of what astronomers loosely call ices, water and ammonia and methane, in forms found nowhere in an ordinary kitchen, wrapped in thick atmospheres of hydrogen and helium. They are worlds of fluid and haze, without any solid surface a traveler could stand upon. Uranus was also the first planet ever found that the ancient skywatchers did not already know. The worlds out to Saturn are bright enough to see with the unaided eye, and every early civilization tracked them across the sky. Uranus sits at the very edge of naked eye visibility, a faint point easily mistaken for a dim star, and it was only recognized as a planet in the age of the telescope. It arrived in our maps as a genuinely new world, the first to widen the known family of the Sun beyond the planets of antiquity. For a long while after its discovery, Uranus kept the secret of its posture. From so far away, it showed only as a small, featureless disk, and the extreme tilt of its axis was not obvious at first. It took patient observation, and eventually the tracking of its moons, to reveal that this distant world was not standing like the others, but lying flat. When that fact came clear, it turned Uranus from a quiet, unremarkable point of light into the strangest of the major planets, the one that broke the simple rule every other world seemed to follow. To grasp how unusual this is, it helps to hold the whole family of planets in mind at once. 8 major worlds circle the Sun, and 7 of them turn on axes that stand more or less upright, tipped by amounts that range from almost nothing to somewhat less than 30 degrees. Only Uranus breaks the pattern, and it breaks it not by a little, but by nearly the full amount possible. A planet can be tipped at most 90 degrees before it is lying flat, and Uranus sits just past that limit. It is not a mild outlier among its neighbors. It is the single exception to a rule the rest of the family keeps faithfully. The rarity of this posture is itself a clue to how it came about. Worlds are born spinning upright because they form from a flat, turning disk of material, and that shared origin gives the whole family its common alignment. For a planet to end up lying on its side, something must have reached in after its birth and changed it, and such events are not common. The very strangeness of Uranus, the fact that it alone lies down, tells us that whatever happened to it was a special event. It was not the ordinary working of nature, but a rare and particular accident in the planet's early life. Tonight, we travel out to that tipped and distant world to ask the oldest question anyone asks about it. What laid Uranus on its side? We will look first at how we can even tell that it lies down, reading the posture of a planet that gives almost nothing away. We will follow its remarkable year, with seasons unlike any other in the Sun's family. And we will come, slowly and without hurry, to the leading answer, an ancient collision at the very beginning of the planet's life, and to the quieter possibilities that still keep the question open. There is no urgency in any of it. The planet has waited a long time to be understood, and it is in no hurry now. Uranus is a difficult world to read, and understanding its tilt begins with appreciating how little it shows. Seen from far off, the planet is a smooth, pale disk softly blue-green, with almost no markings at all. It has none of Jupiter's bold banded storms, none of Saturn's shifting cloud belts. For a long time, this blankness made even the planet's rotation hard to measure, because there were so few features to follow around the globe as it turned. A planet that hides its face does not easily reveal which way it leans. The extreme tilt also shapes what we are able to see of the planet from far away in the first place. For long stretches of the Uranian year, one pole is turned toward the inner Sun's family, and so toward us, which means we spend decades looking down upon a single hemisphere of the planet, while the other remains hidden, turned away into its long night. Only near the equinoxes do we come to see the planet more nearly from the side, with its equator facing us and both hemispheres brought into view. Our very perspective on Uranus is governed by its posture, shifting slowly across the planet's long season. A feature near one pole may be well placed for viewing during one long stretch of years, and then carried out of sight as the planet turns its face away. Those who study Uranus must therefore be patient not only with its faintness, but with its changing presentation, waiting for the slow wheel of its seasons to bring the regions they wish to see back into view. The planet does not merely lie on its side. It shows us that side, and then the other, on a schedule measured in decades. The rotation, once measured, came out to roughly 17 hours for a single turn, in that slow backward sense the tilt implies. But the angle of the axis, the fact that the planet lies almost flat, could not be read from the bland disk alone. It had to be found another way. The clearest evidence came not from the planet itself, but from everything gathered around it, from the moons and rings that circle the world and betray the direction of its spin. A planet's moons and rings tend to travel around its equator, riding in the same plane as the planet's own turning. This is a general rule across the Sun's family, a natural consequence of how worlds and their satellites form together from a spinning disk of material. Saturn's bright rings lie above its equator. Jupiter's major moons circle close to its equatorial plane. If you know where a planet's moons ride, you know where its equator lies, and from that, you know how the planet is tilted. Uranus keeps this rule faithfully. Its moons and rings orbit above its equator, just as they should. But because the planet is tipped almost onto its side, that equator is tipped too, and so the entire system of moons and rings is tilted along with the world. The family does not circle a level waist around an upright planet. It wheels around a planet lying down, sweeping up over one pole and down past the other, orbiting in a plane turned nearly on end, relative to the planet's path around the Sun. From our vantage point far away, this produces a picture found nowhere else. Over the long course of the planet's journey around the Sun, we sometimes see its moon system nearly face-on. When we do, the moons trace out a set of neat, concentric circles, one inside the next, like the rings of a target or the pattern on a dartboard, centered on the pale disk of the planet. A world with an ordinary upright axis never shows this. Its moons, seen from the side, would appear strung out in a line across its middle. The circular, nested pattern is the unmistakable signature of a planet tipped onto its side. At other points along the orbit, the same system turns edge-on to our view, and the neat circles collapse into a single thin line, the moons and rings seen along their own plane. As the decades pass and Uranus moves along its orbit, the appearance shifts slowly between these two extremes, from the open target to the closed line and back again. This slow change, playing out across the length of a human lifetime, is the planet quietly showing us the angle of its axis if we are patient enough to watch. The rings themselves told the same story, and they were found in a way that suited so understated a planet. The rings of Uranus are nothing like the broad, bright bands of Saturn. They are narrow, dark, and faint, thin threads of shadowed material easily missed. They were first noticed not by seeing them directly, but by watching what they did to the light of a distant star. As the planet drifted in front of that star, the star's light blinked out and returned several times over, once for each narrow ring, both before the planet itself crossed the star and again after. That repeated winking of starlight revealed a whole system of thin rings, and the pattern of the blinks showed how the rings were oriented, tipped nearly on end, riding the same tilted equator as the moons. There is a quiet elegance in learning a planet's posture this way, by watching the shadows of its rings fall across a distant star. Uranus does not announce itself. It does not show bold storms or bright bands. It gives up its secrets slowly, through the patient tracking of faint moons and fainter rings, through the blinking of starlight and the slow shifting of a target pattern across the years. To read this planet at all is to learn to read gently, to gather small signs over long stretches of time. All of these small signs point the same way. The moons ride a tilted equator. The rings ride the same tilted plane. The whole system is turned nearly on end. Behind every one of these observations stands the same conclusion, reached not from a single dramatic image, but from the slow accumulation of quiet evidence. This distant, featureless, pale blue-green world is not standing upright like its neighbors. It is lying on its side, and it has arranged its entire family of moons and rings around that fact. It is worth appreciating how much patience this kind of knowledge demands. A planet does not announce its tilt in a single image. The angle of an axis lying nearly flat must be pieced together from many observations gathered over long stretches of time, from the slow wheeling of moons, from the shifting appearance of a ring system, from the way the whole arrangement opens and closes across the years. No single measurement settles it. The conclusion emerges from the accumulation of many, each one a small confirmation, until the picture becomes certain. This is how much of astronomy proceeds, and there is a calm discipline in it. The universe rarely hands over its facts all at once. It offers them slowly, in fragments, to those willing to watch and wait and gather. The posture of Uranus was learned in just this way, not seized in a moment, but assembled patiently, sign by sign, from a distant world that gives almost nothing away at a glance. To know that it lies on its side is to have earned that knowledge through the long, unhurried labor of watching. Knowing that a planet lies down and knowing why are two very different things. The posture can be read from the sky with patience. The cause is buried in a past far older than any telescope, in an era when the planet was young and the space around it was crowded and unsettled. To reach for that cause, we first have to follow what the tilt does to the planet now, across the long and unusual year that lying down creates. For the tilt is not only a matter of arrangement. It shapes the very rhythm of light and dark on this world, in a way that has no equal anywhere else in the Sun's family. Uranus takes about 84 Earth years to travel once around the Sun. It moves along a wide, slow orbit far out in the cold, and a single circuit spans most of a long human life. On a planet with an ordinary upright axis, a year that long would still bring fairly familiar days. Sunrise and sunset would march around the globe with each rotation, and sunlight would be shared, more or less evenly, between the two hemispheres through the turning of the year. But because Uranus lies on its side, its year unfolds unlike anywhere else the Sun's light reaches. For a large part of its orbit, one of the planet's poles points almost directly toward the Sun, while the other points away into the dark. This is the strange consequence of a world tipped nearly flat. The pole facing the sun sits in continuous daylight, with the sun wheeling in slow circles overhead and never setting, day after day, year after year. The opposite pole, at the same time, is turned fully away, locked in an unbroken night, with the sun nowhere in its sky at all. Because the whole orbit lasts about 84 years, and because the planet spends the first stretch of it leaning one pole toward the sun and the later stretch leaning the other, each pole passes through roughly 42 years of continuous sunlight, and then roughly 42 years of continuous darkness. Consider that for a moment, gently. On the sunlit pole of Uranus, the sun does not rise and set. It simply circles, low and pale, for a span of time longer than many human lives, before the slow motion of the planet along its orbit finally carries that pole around toward its long night. Only near the midpoints of the journey does something more familiar return. As Uranus rounds the parts of its orbit between these extremes, it reaches its equinoxes, when the sun climbs to shine down over the planet's equator rather than one of its poles. For that stretch of the long year, the more ordinary rhythm briefly comes back. As the planet turns on its 17-hour spin, sunlight sweeps across the whole globe, and day and night chase one another around the world much as they do on Earth, though far more dimly and far more quickly than they do here. This means that the pattern of light on Uranus changes character completely across its year. For decades at a time, the planet knows only steady day at one pole and steady night at the other, a world divided into a lit half and a dark half that barely change. Then, near equinox, that frozen arrangement dissolves into a brief season of rapid days and nights spread across the whole planet. Then it slowly freezes again, the other way around, with the once dark pole now turned to face the sun for its own long summer of unbroken light. No other planet in the sun's family lives a year shaped like this. You might expect such an arrangement to tear the planet into extremes of temperature. If one pole soaks in decades of continuous sunlight, while the other endures decades of darkness, surely the two ends of the world should differ enormously in warmth. And yet they do not. This is one of the quiet surprises of Uranus, and one of the puzzles the tilt leaves behind. Careful measurements show the planet to be remarkably even in temperature from equator to pole. The sunlit pole is not the runaway warm spot the simple geometry seems to promise. The explanation seems to lie in the atmosphere, which must move heat around the planet efficiently enough to smooth out the enormous imbalance in sunlight. Somehow the winds and the slow circulation of the air carry warmth from the long-lit hemisphere toward the shadowed one, keeping the whole planet close to a single temperature. Exactly how it manages this so thoroughly, on a world whose interior gives off almost no heat of its own to help stir the air, is not fully understood. The evenness is measured and real. The complete account of it is still being worked out. The tilt even seems to govern when Uranus has weather at all. The one spacecraft ever to pass close by arrived near one of the planet's solstices, when a pole was turned toward the sun, and much of the world was locked in its long, steady day or its long, steady night. It found a nearly featureless planet, a smooth, pale ball with almost nothing to see, so quiet that it seemed a rather uneventful world. That single quiet portrait shaped how the planet was pictured for a long time afterward. But as Uranus swung onward toward its equinox, and sunlight began once more to reach across both hemispheres, watchers with patient telescopes saw the planet's weather stir. Bright clouds of high, cold material appeared and brightened. Faint banding emerged. A dark spot of the kind seen on the other giant planets came and went. The world had not changed its nature between one season and the next. The changing angle of sunlight had simply woken a weather that the earlier, quieter portrait had missed. Uranus is a more active planet than that first calm glance suggested. We had merely caught it sleeping. There is a further consequence of this arrangement worth pausing over. On Uranus, the very meaning of a day changes with the seasons. Near equinox, when the sun crosses the equator, a day is much like a day anywhere, the roughly 17-hour turn bringing light and dark in steady succession across the whole planet. But near solstice, with a pole held toward the sun, that same 17-hour rotation no longer brings sunrise or sunset to the polar regions at all. The sun simply circles the sky, wheeling around without touching the horizon, while the planet turns beneath it. The rotation continues, faithful as ever, but the day it would produce has been erased by the tilt. So the length of a day on Uranus depends entirely on where one stands and when one asks. At the equator near equinox, days and nights come and go quickly. At a pole near solstice, there is no day at all, only a long unbroken light or a long unbroken dark stretching across decades. The planet keeps a single steady spin, and yet, because it lies on its side, that one rhythm is stretched and folded into seasons that share almost nothing with one another. It is a world where the meaning of morning is not fixed, but depends on the slow turning of the years. So the tilt is not only a matter of how the moons are arranged, or how the planet appears from far away. It reaches into the very rhythm of the world, setting the length of its days and the shape of its seasons, governing where the sunlight falls and even when the winds rise. A planet, knocked onto its side, does not merely look unusual. It lives an unusual life, on a schedule of light and dark that belongs to no other world. And all of it, the 42-year days, the even temperature, the weather that wakes at equinox, follows from that one ancient event we have not yet named. It is time now to ask directly what could tip a whole planet over. The question that gives this night its shape is simple to ask and hard to answer. What tipped Uranus over? A planet does not lie down on its own. Worlds are born, spinning upright, more or less, inheriting the direction of the great turning disk of gas and dust, from which they and their star first formed. To find one lying on its side is to find a world whose original posture was changed, and changing the posture of a planet is no small thing. Something had to reach in and turn this world nearly on end, and the leading answer is also the most forceful one. Most astronomers who study the problem favor a collision. Early in the history of the Sun's family, when the planets were still young and the space around them was crowded with leftover bodies, Uranus is thought to have been struck by something very large. The suspected culprit is a protoplanet, a world in its own right, perhaps holding 1 to several times the mass of the Earth, on a path that crossed the young planet's own. It arrived at an angle, delivering an off-center blow, and that glancing impact turned the whole planet over. To feel why the collision had to be so large, it helps to think about what a spinning planet is. A world the size of Uranus, turning on its axis, carries an enormous store of what physicists call angular momentum, the persistence of its spin. That store resists any attempt to change it. A spinning top stays upright precisely because its spin resists being tipped. To reorient a planet by nearly 90 degrees, then, is to overcome that resistance, and to do so requires delivering a comparable store of angular momentum from the outside, in a different direction. Only a genuinely massive body, arriving at speed and off to one side, can supply so much in a single event. Uranus holds about 14.5 times the mass of the Earth, and it is that great inertia the impactor had to overcome. A small body could not have done it. A pebble, a mountain, even a moon-sized world hitting the planet would have left the tilt essentially unchanged, a minor nudge lost in the planet's steady turning. It took something on the scale of a small planet, one of the many that are thought to have wandered the young sun's family before the worlds settled into their final places, to lay Uranus down. Computer simulations of such a collision, tracking the physics of the strike, are able to reproduce a final tilt close to the 98 degrees we actually measure. What the impactor itself was made of, and where it came from, we can only reason about. In the outer reaches of the young sun's family, the large bodies would have been worlds of ice and rock, akin in a broad way to the material of Uranus itself, gathered from the same cold region of the forming system. The striker was likely such a body, a protoplanet of ice and stone that had grown large in the outer dark and then wandered onto a path that crossed the young planet's own. It was not an alien thing from far away, but a sibling of a kind, one of the many worlds the outer sun's family was building at the same time, most of which were swept up or cast out before the planets reached their final number. That so large a body should have been available to strike is not surprising for the era. The young outer system held many more sizable worlds than survive today, and their crossing paths made great collisions a real, if uncommon, possibility. Uranus met one of them, and wears the mark of that meeting still. There is a genuine and unsettled debate over whether it took one impact or several. A single giant strike, delivered off-center, is the simplest idea, and it tips the planet efficiently. But a single massive blow tends to do more than tip. It tends to spin the planet up to a rapid rotation, and to pour tremendous energy into it, heating the whole world severely. Some researchers, weighing the details, prefer a scenario in which two or more smaller impacts arrived over time, their separate effects adding together to produce the same large tilt, while leaving the planet turning at the more moderate rate we see today. Both pictures, the single great blow and the several smaller ones, share the same essential core. Uranus was reoriented by collision. It did not drift into its sideways posture gently, and it was not born that way. Something struck it, once or more than once, hard enough to turn a world holding many times the Earth's mass onto its side. The differences between the versions are real and interesting, and they change the details of what the planet endured, but they agree on the central event. This world was knocked over. The timing of that event is placed very early, during or just after the era when Uranus was finishing its formation, still gathering the last of the material that would make it whole. At that stage, the space around the young planet was still busy, with large bodies traveling on crossing paths, the unfinished pieces of the outer sun's family. Collisions between such bodies, while never common, were far more likely then than they would ever be again. The sun's family was a rougher place in its youth, and worlds still bore the marks of that roughness. Uranus simply bears the largest mark of all. Whatever struck it did so once, near the beginning of everything, and the planet has carried the tilt ever since. This is worth holding on to, because it changes how the fact feels. The collision is not a recent thing, nor an ongoing one. It happened at the dawn of the sun's family, in an age so far removed from now that the numbers lose their meaning. And in all the enormous time since, through the slow forming of the other worlds and the long settling of their orbits, Uranus has simply gone on turning on its side, quietly, without further incident. The blow was brief. The stillness afterward has lasted almost forever. It is worth setting this event beside a more familiar one to feel its scale. Our own world is thought to have suffered a giant impact early in its history, a collision with a body that threw off the material from which the moon later formed. That single event shaped the Earth and gave us our companion in the sky. The blow that tipped Uranus belongs to the same class of ancient event, a collision between worlds in the crowded youth of the Sun's family. Such events were the finishing strokes of planet building, the last great impacts as the worlds swept up the final large bodies around them. Seen this way, the tilt of Uranus is not an oddity standing outside the ordinary story of how planets form. It is a particularly clear example of a process that touched many worlds. The young Sun's family was assembled through collision, small bodies joining into larger ones merging in great impacts, until the planets we know had gathered themselves from the debris. Most of those impacts left no lasting sign we can easily read. The one that laid Uranus down left the plainest sign of all. A whole world turned on its side, the violence of planet building written across the posture of an entire planet. There is a strange calm in that thought. We tell the story of Uranus as a story of collision, and the collision is real, and it was surely a hard and consequential event. But from where we stand, looking out at the planet now, there is no sign of struggle. There is only a pale, cold world rolling slowly through the dark, long past whatever happened to it. The violence is entirely in the past tense. What we see is the long, patient aftermath, a planet that was laid down at the beginning and has rested on its side, undisturbed, through an unimaginable stretch of time. A collision forceful enough to tip a planet onto its side sounds like the kind of event that should leave chaos in its wake. We might expect the world around such a planet to be a jumble, its moons scattered onto tilted and crossing paths, its rings torn into disorder. And yet the system around Uranus is not a jumble at all. Its major moons circle the planet in neat, nearly circular paths, closely aligned with one another, riding smoothly in the tilted equatorial plane and moving in orderly step with the planet's spin. At first consideration, this tidiness looks like a problem for the whole idea of a collision. The difficulty is worth stating plainly, because it is a real one. If Uranus had been struck and tipped over after its moons were already in place, those moons should have been left behind. They would have kept circling in their original plane, around the direction the planet used to spin, indifferent to the sudden reorientation of the world at their center. Tipping the planet would not automatically drag its moons along with it. We would expect, in that case, to find the moons badly out of line with the planet's new, tilted equator, a family orbiting one way around, a world now leaning another. Instead, the moons match the tilted equator almost perfectly. They lie exactly where a planet tipped along with them would place them. The favored answer turns this puzzle into one of the strongest pieces of evidence for the collision. A giant impact would not merely knock the planet over. It would blast an enormous quantity of vaporized rock and ice off the planet and its striker, hurling that material into the space around the world, where it could not simply fly away. Held by the planet's gravity, the debris would settle, over time, into a broad, flattened disk. And here is the essential point. That disk would settle around the planet's new tilted equator, because the plane of a spinning planet's equator is set by the direction of its spin, and the spin was exactly what the collision had just changed. Out of that settling disk of debris, over a long span of time, moons would gather and grow. Small particles would collide and stick, building larger bodies, which would sweep up more material and grow larger still, until a family of moons had formed from the ring of wreckage the impact threw off. And because that disk lay in the planet's new equatorial plane, the moons born from it would inherit that plane. They would circle the tilted equator, not because they somehow followed the planet as it tipped, but because they were made, afterward, from material that already shared the planet's new orientation. In this picture, the moons are younger than the tilt. They are not survivors that impossibly kept pace with a toppling world. They condensed later, out of the debris of the very collision that laid the planet down, and so they naturally came to rest in the tilted plane. Their orderly, aligned, gently tilted orbits are precisely what such a history predicts. Simulations that follow an impact and then track the settling of its debris disk are able to produce a moon system very much like the one Uranus actually possesses, tidy and tilted together. The neatness that first seemed to argue against a collision turns out to be one of its clearest fingerprints. It is worth distinguishing the orderly inner moons from the smaller, more distant ones that also attend the planet. The major moons and their near companions ride the tilted equatorial plane in tidy, near-circular orbits, and it is these that carry the clearest record of the planet's history. Farther out, move a scattering of smaller moons on paths that are more tilted and more stretched, and some of these are thought to have been captured later, drawn in from elsewhere, rather than formed in place. This division between orderly and captured moons is common among the giant planets, each of which keeps a tidy inner family and a looser outer company. On Uranus, it is the inner family that shares the planet's tilt so faithfully, and that faithfulness is the clue. The captured outsiders followed their own separate paths into the system and need not agree with the planet's posture. The inner moons, born with the planet or from its debris, agree with it completely, and in that agreement lies the evidence. Even in versions of the story where some of the moons existed before the impact, the same reasoning can hold. A young planet still surrounded by a disk of gas and dust, in the act of forming its moons, would have that surrounding disk pulled toward the new equatorial plane after the strike. The growing moons, embedded in the disk, would be carried along with it into the tilted arrangement. Whether the moons formed entirely from impact debris or were shepherded into place by a disk that responded to the collision, the outcome is the same, and it matches what we see. So the tidy, tilted family of moons is not evidence against a violent beginning. It is one of the clearest records we have that a violent beginning, followed by a long and gentle settling, is what took place. The moons remember the collision, in a sense, by lying exactly where the collision would have set them. To look at their orderly circles around the tipped planet is to look at the calm that formed in the aftermath of the blow, the debris of an ancient impact gathered patiently into worlds, all of them keeping faith with the planet's new posture. The timescales involved in this settling are worth holding in mind because they soften the violence of the picture. The collision itself would have been brief, over in a matter of hours, as worlds do their work upon each other. But the gathering of the debris into moons, the patient condensing of scattered material into ordered bodies, would have taken a great span of time afterward, unfolding slowly across an age. The disorder of the impact was momentary. The order that followed was built gradually, particle joining particle, over a stretch of time long enough to turn wreckage into worlds. This is why the system looks so calm today despite its beginnings. We are not seeing the collision, nor its immediate aftermath, but the long, quiet result of an age of settling. The moons have had time beyond measure to smooth their orbits, to round their paths, to find the stable arrangement they now keep. What began as a scattered ring of debris has become, through nothing more than patience and gravity, a tidy family of worlds circling in a shared and gentle plane. The planet's household was not born calm. It became calm, slowly, in the long quiet that followed the blow. There is something quietly moving in that idea, if we let ourselves feel it. The moons of Uranus may be, in part, the reassembled pieces of an old catastrophe, the scattered material of a collision drawn slowly back together into gentle, ordered orbits. What began as wreckage became a family. The planet was struck and knocked over, and out of the very ruin of that event, over a length of time beyond easy imagining, new small worlds took shape and settled into place around it. The disorder did not last. Order gathered itself again from the fragments, and it has held ever since. That order still holds today. The moons of Uranus continue to trace their neat, tilted circles, sweeping up and over the planet's poles in a plane turned nearly on end, exactly as they have done since they first formed. They carry the memory of the collision not as damage, but as arrangement, in the very geometry of their paths. And they will go on tracing those circles, patiently, long after this night has passed and been forgotten, keeping the planet company in the long dark at the edge of the Sun's family. To understand a planet's history, it helps to know what the planet is made of, and Uranus is made of things that behave strangely far below its clouds. There is no solid ground anywhere on this world, no surface a traveler could ever stand upon. To descend into Uranus would be to pass from thin, cold air into ever thicker and hotter fluid, the pressure rising without pause until the very idea of an outside and an inside blurs into a single graded body of matter. The planet is not a ball of rock wrapped in air. It is a great sphere of fluid and haze, sorted loosely by weight from its outer edge to its center. The outermost layer is the atmosphere, a mixture of hydrogen and helium, the same light gases that make up most of the Sun and the giant planets. Within that atmosphere, higher up, floats a smaller amount of methane, and it is this methane that gives the planet its color, though the gases beneath it stretch far down before they change their nature. As one descends, the air grows steadily denser and warmer, the pressure mounting until the gas is squeezed into a fluid, and the boundary between atmosphere and interior arrives without any sharp line to mark it. Below the outer envelope of hydrogen and helium lies the layer that gives the ice giants their name. Astronomers call it ice, but the word is misleading, and it is worth setting the ordinary meaning aside. This is not cold, solid, skatable ice. It is a hot, dense, churning fluid made largely of water, ammonia, and methane, held under such enormous pressure that it takes on forms found nowhere in everyday life. The term ice refers to the chemical makeup, the kinds of molecules involved, rather than to anything frozen. Far down inside Uranus, these ices form a slushy, electrically conductive ocean of a kind the surface of the Earth never sees. The pressures at these levels are difficult to hold in the mind. The weight of the entire planet above presses down on the material below, compressing it beyond anything our instruments can easily reproduce. Under such conditions, familiar substances are forced into unfamiliar states. Water does not behave as the water in a glass behaves. It is squeezed and heated into exotic phases, dense and strange, part liquid and part something else, conducting electricity as a metal would. The interior of Uranus is a place where the ordinary rules of matter give way to the rules of extreme pressure. One of the more remarkable ideas about these interiors concerns carbon, and it has a certain quiet beauty. The methane far down inside the planet contains carbon, and under the crushing pressures and high temperatures of the mantle, that methane can be broken apart. The carbon freed in this way may be squeezed together into crystalline form, into what is, in effect, diamond. If the idea is correct, then far below the pale clouds of Uranus, diamonds may form and then sink, drifting slowly downward through the surrounding fluid toward the center of the world, a slow settling of precious stone into the dark. It is a strange and lovely thought, a rain of diamond falling forever through the inside of a planet. At the very center of Uranus, beneath the layered fluids, there is thought to be a core of heavier material, rock and metal, perhaps roughly the size of the Earth itself. This core is not a place of any calm we would recognize, held as it is under the full weight of the planet and heated by the pressure. But it is the densest and innermost part of the world, the seed around which the rest of the planet is arranged. Whether it is sharply bounded or blends gradually into the ices above it is one of the many things we do not yet know for certain about this distant world. We might reasonably ask how any of this can be known, given that no one has ever seen the inside of a planet. The answer is that a world's interior can be read indirectly from the outside. The total mass of Uranus can be measured by the way it pulls on its moons and on passing spacecraft, and its size can be measured directly, and from these two together, we learn its overall density, how tightly its material is packed. That density, lower than solid rock but higher than the light gases alone, tells us the planet must be made largely of the intermediate materials we call ices, layered beneath a lighter atmosphere. The finer details are filled in by physics and by careful modeling. The way the planet's gravity varies, the behavior of its magnetic field, the manner in which it responds to the pull of the sun and its moons, all place limits on how the mass inside must be arranged. From these clues, and from what is known of how water and ammonia and methane behave under great pressure, a picture of the interior is built, tested against every measurement we can make. We have never seen inside Uranus, but we can reason our way inward with real confidence, guided by the evidence the planet offers from without. The arrangement of these interior layers matters for our story because it connects to the tilt and to the collision in a subtle way. The way heat moves through a planet depends on how its interior is structured, on whether the material within churns and circulates or lies in still, settled layers. A planet whose interior stirs, carrying hot material up and cool material down, leaks its inner warmth steadily to the surface. A planet whose interior is sorted into stable, unmixing layers holds its warmth far more tightly, letting little of it escape. The structure inside Uranus and how the ancient collision may have shaped it is bound up with one of the planet's other puzzles, which we will come to shortly. For now, it is enough to picture the world beneath the clouds. Uranus is a graded sphere of matter, thin cold gas at its edge, thickening into a hot ocean of exotic ices, perhaps raining diamond in its middle depths, settling to a rocky core near its center. It has no shore, no ground, no place to stand. It is fluid nearly all the way through, a world one could never land on but only sink into, growing hotter and denser with every mile, until the descent ends at a small hot core wrapped in the weight of an entire planet. A traveler attempting to descend into Uranus would find no moment at which they had arrived. They would pass from the thin, cold upper air into steadily thickening haze and cloud, the light failing around them, the pressure mounting without pause. There would be no surface to meet, only fluid growing ever denser, the temperature climbing from its bitter cold at the top toward great heat far below. At no point would there be a floor, a shore, a boundary to stand upon. The descent would simply continue, the surroundings closing in and warming, until the traveler was part of the graded body of the planet itself. This is what it means to call Uranus a giant planet rather than a rocky one. It is not a ball of stone wrapped in a thin skin of air, but a great fluid world, gaseous at its edge and dense within, with no solid face turned to the sky. This is the body that was struck and tipped over long ago. When we speak of a collision laying Uranus on its side, this is what was reoriented, not a solid ball, but a great sorted sphere of fluid and haze, turned nearly on end and left to settle. Understanding that the planet is fluid to its center helps make sense of how a single event could have arranged so much of what we now see, from the tilt of its axis to the missing warmth of its interior. To that missing warmth, one of the quietest and most telling of the planet's mysteries, we turn next. There is a second oddity about Uranus, quieter than the tilt but perhaps sharing the same cause. Uranus is the coldest world in the entire family of the Sun, at least at the top of its atmosphere. Its cloud tops fall to around 49 degrees above absolute zero on the scale astronomers use, which is roughly 224 degrees below zero on the Celsius scale, a cold beyond anything in ordinary human experience. What makes this remarkable is not merely that it is cold. It is that Uranus is colder than Neptune, even though Neptune orbits far beyond it, out where the Sun is fainter still, and its warmth even thinner. This should not be. The giant planets are not warmed by sunlight alone. Each of them still holds a store of heat left over from its formation, the warmth of the gravitational gathering that made it, and each slowly leaks that inner heat outward into space. This internal warmth is a normal feature of a giant world, the lingering glow of its own creation. And Neptune, farther from the Sun and receiving less of its light, shows this inner heat clearly. Neptune radiates well over twice as much energy as it receives from the Sun, glowing from within, warmed far more by its own interior than by the distant star. Jupiter does the same, and so does Saturn. Each of the giant planets, when its energy is carefully accounted, is found to be giving off more heat than it takes in from sunlight, the surplus coming from within. This is simply what giant planets do. They are still slowly releasing the warmth of their formation, cooling by degrees across the long life of the Sun's family, leaking their inner fire into the cold around them. It is one of the expected signatures of a world of their kind. Uranus does not do this. When its energy is measured, the planet is found to radiate almost exactly as much heat as it receives from the Sun, and very little more. Its internal warmth, the leftover heat that every other giant is still steadily releasing, appears to be either nearly gone or somehow sealed away where it cannot escape. On a planet otherwise so similar to Neptune, its near twin in size and make, this is a glaring difference, and it demands an explanation as much as the tilt does. Two worlds so alike should not differ so sharply in something as basic as their inner heat. A giant collision offers a way to account for the missing warmth, and it does so through two possibilities that need not exclude one another. In the first, the collision itself drove much of the planet's original heat out in a single catastrophic release. A strike large enough to tip the planet would have poured immense energy into it, and in the upheaval that followed, the primordial warmth stored in the young world could have been largely expelled, radiated away in the aftermath of the blow. Uranus, in this telling, spent its inheritance of heat in one event and has been running cold ever since. In the second possibility, the collision did not empty the planet of heat so much as trap it. A strike could have rearranged the planet's interior into stable, settled layers that do not churn and mix. On the other giants, as we have seen, hot material rises and cool material sinks, and this stirring carries heat steadily outward to the surface where it escapes. But if Uranus's interior was left sorted into still, unmixing layers, that circulation would be suppressed. The heat remaining in the far interior would be unable to rise, sealed beneath layers that will not carry it up. The surface would then appear cold, not because the warmth is gone, but because it is locked away, unable to reach the outside. These two ideas, the heat expelled and the heat trapped, both trace the planet's coldness to the same ancient event that laid it on its side. And this is why the tilt and the cold are so often told as a single story. They are two anomalies on the same world, two ways in which Uranus departs from what its near-twin Neptune shows, and the simplest account is that one cause lies behind both. The collision that tipped the planet is also, plausibly, the reason its inner fire fell quiet. To see why a settled interior would hold heat, it helps to think about how warmth moves through a fluid. In a stirring, circulating body, hot material is buoyant and rises, carrying its heat upward, while cool material sinks to be warmed in turn. This churning, which physicists call convection, is a remarkably efficient way to move heat from a planet's interior to its surface, where it can escape into space. It is the process by which most of the giant planets shed their inner warmth, and it keeps their interiors and their atmospheres in slow, steady communication. If the interior of Uranus is instead sorted into stable layers, this churning cannot occur. Layers of differing composition, arranged with the denser material below and the lighter above, resist mixing. A parcel of warm fluid far inside cannot simply rise, because to rise it would have to push into a layer lighter than itself, and it lacks the buoyancy to do so. The heat is held in place, unable to travel upward, sealed beneath the stable layering. Across an age, such a planet would appear cold at its surface, while remaining warm far within, its inner heat present but imprisoned, quietly held rather than truly lost. The comparison with Neptune is the cleanest test we have, and it is worth dwelling on. Here are two worlds, close in size, close in mass, made of much the same materials, formed in the same outer reaches of the Sun's family. By every reasonable expectation, they should be near siblings in behavior as well as in make. Yet one of them glows with the warmth of its own interior, and the other barely does. One of them stands broadly upright, and the other lies on its side. The differences cluster on the same planet, on Uranus, and they point together toward a history that Neptune did not share, a singular, violent event in the youth of the tilted world. We cannot yet say with certainty which version is right, whether the heat was thrown out long ago or remains trapped far down inside even now. Both are consistent with what we can measure from afar, and telling them apart would require the kind of close, patient study that only a visiting spacecraft could provide. But the coincidence itself is telling. Two great oddities, the tilt and the missing heat, resting on the same world, absent from its twin. It is hard not to read them as chapters of one story, the long consequences of a single blow struck at the beginning of everything, still shaping the planet in the cold and the quiet, an age beyond counting later. For all its strengths, the story of a great collision is not the only idea, and it is not proven. It is worth being honest about that, because the honesty is part of what makes the question beautiful. We have visited Uranus only once, and only briefly, and much of what we say about its distant past is built on careful reasoning rather than direct sight. The collision is the leading explanation, but the matter is genuinely open, and several quieter alternatives have been proposed, each trying to reach the same tilt without a single catastrophic blow. One idea is that Uranus once had a large moon that it no longer has. A sufficiently massive satellite orbiting the planet can exert a steady gravitational pull that acts on the planet's spin over immense stretches of time. Under the right conditions, this pull can slowly rock the planet's axis and gradually walk it over toward a large tilt, not in a sudden blow, but in a patient accumulation across many millions of years. The effect is strongest when the natural rhythm of the planet's slow wobble happens to match the rhythm of the moon's orbit, a matching that physicists call a resonance, which lets a small nudge build steadily into a large change. In this gentler telling, the tilt grows by degrees, and the moon responsible is later lost, thrown out of the system, or destroyed in the very process that tipped the planet, leaving no obvious culprit behind for us to find. The appeal of this idea is that it tips the planet without the tremendous heating a giant impact would bring, which sidesteps some of the difficulties of the collision story. Its weakness is that it requires a large moon that must first do its work and then conveniently vanish, and evidence for such a lost moon is not easy to come by. It is an elegant idea that asks us to believe in something that is no longer there. Another possibility ties the tilt to a grand episode in the history of the whole Sun's family. There is good reason to think that the giant planets did not form exactly where they now orbit, and that early in their history they shifted, moving inward and outward before settling into their present arrangement. During such a migration, as Uranus's orbit slowly changed, the rhythm of the planet's own axial wobble could have been swept into a resonance with some other slow cycle in the system. Once caught in that resonance, a small initial tilt could have been pumped up gradually into the large one we see. This too can tip the planet without a collision, provided Uranus had a broad disk of surrounding material or a substantial moon to give the effect enough leverage to work. These gentler ideas have real merit, and serious researchers continue to explore them. They remind us that a planet's posture can be changed by patient gravity as well as by sudden force, that the slow tug of a moon or the long sweep of a migrating orbit can, given enough time, accomplish what we might imagine requires a blow. The Sun's family is old enough, and its history rich enough, that such quiet mechanisms have had ample time to act. Not every dramatic outcome requires a dramatic cause. Neptune, once again, serves as the quiet control in this experiment. It formed in the same outer region, of much the same material, and grew to nearly the same size, yet it stands broadly upright, tilted by a modest amount, much like the inner worlds. Whatever tipped Uranus, then, was not something that happened to ice giants in general. It was particular to Uranus, an event or a process that touched the one planet and spared its twin. This is a strong constraint on any explanation. It must account not only for why Uranus lies on its side, but for why Neptune, so similar in nearly every other way, does not. The collision story meets this test easily, since a chance impact would strike one world and miss another. The gentler mechanisms must work harder to explain why they acted on the one planet alone. That single difference between the twins, upright and tipped, is perhaps the sharpest clue the pair provides, and any full account of Uranus must answer to it. Still, the collision remains the frontrunner, and the reason is a matter of economy. A single great impact explains three things at once, with one event. It accounts for the extreme tilt. It accounts for the tidy, tilted family of moons, which could have formed from the debris the impact threw off. And it accounts for the strangely cold, quiet interior, which the same blow could have emptied or sealed. The gentler alternatives can each explain the tilt on its own, but they have a harder time explaining the moons and the missing heat in the same breath. A collision ties the whole knot of oddities together into a single history, and there is a persuasive simplicity in that. Science often favors the explanation that accounts for the most with the least, and by that measure, the collision leads. But leading is not the same as proven, and a careful mind holds the alternatives open. It may yet turn out that Uranus was tipped by the slow work of a vanished moon, or by a resonance swept up in the migration of the giant worlds, rather than by a single strike. Or it may be that more than one process played a part, that the truth is a mingling of the sudden and the gradual. The planet has not told us plainly, and we should not pretend it has. There is a particular pleasure in a question that remains genuinely open, and it is worth naming. In an age when so much seems already settled, Uranus offers a real and honest mystery, a plain fact whose cause we cannot yet fully explain. This is not a failure of science, but one of its quieter gifts. The planet marks the edge of what we know, the place where careful reasoning has taken us as far as it can, and where only new evidence can carry us further. To sit with that edge, unhurried, is its own kind of pleasure. The competing explanations also remind us that nature is not obliged to be simple. We prefer the single collision because it explains the most with the least, and that preference is a sound one. But the true history of Uranus may be more tangled than any single story, a mingling of sudden and gradual causes working together across the planet's early life. The honest answer is that we hold several possibilities open at once, weighing them, favoring one, but closing the door on none. There is a kind of maturity in that patience, a willingness to let the question stay a question until the planet itself offers us more to work with. What we can say is that Uranus is keeping the finer details of its own accident to itself, at least for now. We know that it lies on its side. We have strong reasons to think a collision is the likeliest cause, and strong evidence in the arrangement of its moons and the coldness of its interior. But the full and certain story, the exact how and when, remains just out of reach, waiting for a closer look than we have yet managed. There is no shame in that uncertainty. It is simply the honest edge of our knowledge, the place where reasoning has carried us as far as it can, and where only a return to the planet itself can carry us further. The tilt of its axis is not the only thing about Uranus that sits at a strange angle. The planet also generates a magnetic field, as the other giant worlds do, and that field is peculiar in ways that deepen the sense of a world where nothing quite lines up. A magnetic field is, in a sense, a planet's invisible compass, a structure of magnetic force surrounding the world and reaching out into space. On most planets that carry one, the field is broadly organized around the axis of the planet's spin, its magnetic poles sitting reasonably close to its rotational poles. On Uranus, this tidy arrangement breaks down. The magnetic field of Uranus is tilted by about 59 degrees away from the planet's spin axis. This is an enormous misalignment. On Earth, the magnetic poles lie fairly close to the geographic ones, near enough that a compass is a useful guide, and the field is roughly organized around the same axis the planet turns on. On Uranus, the magnetic axis and the spin axis point in dramatically different directions, leaning away from each other by more than half a right angle. The planet's invisible compass does not agree with its rotation at all. Stranger still, the field is offset. On a well-behaved planet, the magnetic field appears to be generated near the center of the world, so that the field is roughly symmetric around the middle. The field of Uranus is not centered in this way. It appears to arise from a point well to one side of the planet's center, as though the source of the magnetism had been pushed off toward one region of the interior rather than sitting at the core. The result is a field that is both steeply tilted and badly off-center, lopsided in two ways at once. The consequences of this play out as the planet turns. Because the field is tilted and offset, the rotation of Uranus swings the whole magnetic structure around wildly. The magnetic cocoon that surrounds the planet, the region of space where its field holds sway, does not sit steady. It opens and closes and tumbles through each rotation, its shape and orientation shifting as the crooked field is carried around by the spin. Rather than behaving like a steady bar magnet held firm, the field behaves more like something being shaken, wobbling, and reorganizing itself continuously as the planet turns beneath it. Why the field should be so disorderly is thought to be connected to where it comes from. On Earth, The magnetic field is generated in a churning core of molten metal far below the surface, a large and orderly region near the center of the planet. On Uranus, the field is believed to arise not in a central metallic core, but in the layer of exotic ices that makes up much of the planet's interior, that hot, dense, electrically conductive ocean of water and ammonia we considered earlier. If the field is generated in a relatively thin shell of this conductive fluid, rather than in a large central region, the result can be a field that is tilted, off-center, and irregular, exactly the sort of field Uranus displays. Whether this crookedness of the magnetic field has anything directly to do with the great tilt of the planet is not simple to say. The two are different things. The tilt of the axis is a matter of how the whole planet is oriented in space, set by the ancient collision. The tilt of the magnetic field is a matter of how the planet generates its magnetism far within, set by the structure and motion of its conductive interior. They need not share a single cause. And yet both belong to the same broad portrait of a world where the ordinary alignments of a planet have been disturbed, where axis and field and interior all sit at angles that no other planet quite matches. Much of what we know about this crooked field was learned in the hours of the single flyby, when the passing spacecraft sensed the planet's magnetism directly and found it far stranger than expected. Before that encounter, there was no certainty that Uranus even possessed a significant field. The finding of its steeply tilted, off-center magnetism was one of the true surprises of the visit, a revelation that this quiet world was more peculiar than its bland face suggested. Nearly everything we say about the field still rests on those few hours of measurement. The tilted field does what planetary fields do, for all its irregularity. It carves out a protective bubble around the planet, holding off much of the stream of particles that flows outward from the sun, and it channels some of those particles toward the magnetic poles, where they can kindle faint auroras high in the atmosphere. But because the field is so lopsided, and because the planet lies on its side, the way this bubble meets the solar wind shifts strangely through the planet's rotation and through its long seasons. The magnetic surroundings of Uranus are unlike those of any other world, a tumbling, shifting cocoon around a tumbling, tilted planet. It is tempting to wonder whether the collision that tipped the planet also disturbed its interior enough to unsettle the magnetic field, and this is among the questions researchers would like to answer. If the impact rearranged the planet's inner layers, sorting them in unusual ways, it might have shaped the conditions in which the field is generated, contributing to its odd tilt and offset. But this is a possibility rather than an established fact, one more thread that may or may not tie back to the ancient blow. The honest position is that we do not yet know how tightly the crooked compass and the tipped axis are bound together. What we can say is that the magnetic field adds one more item to the long list of things about Uranus that do not stand upright. The axis lies on its side. The magnetic field leans steeply away from that axis and sits off-center besides. The magnetosphere tumbles as the planet turns. Item by item, the planet declines to align itself the way its neighbors do. And all of it deepens the impression of a world made strange at its origin, a world whose every compass, visible and invisible, points somewhere unexpected, keeping its own crooked order out at the cold edge of the sun's family. Of all the things one might notice about Uranus, the first is usually its color. The planet is a soft, pale blue-green, gentle and almost uniform, one of the more soothing hues in the sun's family. It does not glare or burn. It rests in the eye like the color of shallow water seen from above, or of frosted glass lit from behind. That quiet color is not an accident of lighting. It comes from the chemistry of the planet's air, from the way a particular gas, high in its atmosphere, sorts the sunlight that falls upon it. The gas responsible is methane. Present in the upper atmosphere of Uranus, methane has a specific appetite for light. It absorbs the red end of the sunlight that reaches the planet, taking in the warmer tones and holding them, while it allows the blue and green light to scatter back out into space. The sunlight that arrives at Uranus contains all colors mixed together, as sunlight does. But the light that leaves the planet and eventually reaches our instruments has had its reds removed by the methane, and so it carries the cool blue-green cast we see. The planet's color is, in effect, the color of the light that the methane did not keep. Above the main body of the atmosphere sits a layer of haze, and this haze does much to shape the planet's calm appearance. It is a high, thin veil of small particles spread across the top of the air, and it softens whatever lies beneath it. Where another planet might show sharp cloud features and bold contrasts, Uranus shows a smooth and muted face, its details blurred by the overlying haze. The planet looks bland not because nothing is happening within its atmosphere, but because a soft curtain hangs between the activity below and the eye above, gentling everything into a single quiet tone. Beneath that haze, and beneath the methane, the atmosphere continues far down into the planet, thickening steadily. There are cloud layers at different levels, made of different materials as the temperature and pressure change with depth, building a layered sky far more complicated than the smooth outer face suggests. We see only the top of this arrangement, the outermost veil, and it is easy to mistake that placid surface for the whole. But the calm we observe is the calm of the uppermost layer alone. Below it, the atmosphere is a working system of clouds and circulation, hidden from casual view. The planet does have weather, and it does have winds, though they too are largely concealed by the haze. Currents of air move through the atmosphere, some of them swift, carrying clouds along and organizing them into faint bands. Now and then, a brighter cloud rises high enough to be seen through the veil, a patch of white against the blue-green, marking a storm system working below. On rare occasions, a darker feature appears, a shadowed spot of the kind the other giant planets show, drifting through the atmosphere before fading again. The weather of Uranus is real, if understated, a quiet activity beneath a quiet surface. As we noted earlier, this weather seems to answer to the planet's remarkable seasons. When the one spacecraft passed by near a solstice, with the atmosphere in its quietest state, it saw a world nearly without features and reported back a placid, uneventful planet. But as the seasons turned and sunlight spread again across both hemispheres near equinox, the weather stirred, and watchers saw the atmosphere come alive with brightening clouds and shifting bands. The planet's air, it turned out, keeps time with the tilt, growing more active when the light returns to its middle latitudes and quieter when a single pole holds the sun. Even the weather bends to the sideways posture of the world. The color of Uranus becomes more interesting when set beside its near twin. Neptune, made of much the same materials and carrying much the same methane, shows a notably fuller and more vivid blue, while Uranus wears a paler, softer, greener shade. For a long time, this difference was a small puzzle in its own right. Two sibling worlds of similar make wearing visibly different colors. The likely explanation lies in the haze. A thicker layer of high haze over Uranus appears to whiten and soften its color, muting the blue that Neptune shows more openly, lending Uranus its gentler, more washed appearance. So even the planet's color carries a trace of its own character. Uranus is not merely a fainter copy of Neptune. It is a world with its own atmosphere, its own veil of haze, its own quieter shade, set apart from its sibling in appearance, as it is set apart in posture and in warmth. The soft blue-green we see is particular to this planet, the outcome of its own chemistry and its own layered sky. It is one more way in which Uranus, so easily dismissed as the plain and featureless world, quietly declines to be quite like anything else. There is a lesson in that soft blue-green face, if we care to draw it. Uranus looks, at first, like the least eventful of the giant planets, a bland ball with little to show. But that first impression is a kind of trick of the haze, a smoothing over of a world that is, beneath its calm veil, layered and active and strange. The quiet color is genuine, and it is lovely, but it is also a surface. To know the planet only by its placid face is to know only its outermost breath, and to miss the working atmosphere, the exotic interior, and the ancient history that lie beneath. And yet there is something fitting in a world so gently colored being, also a world that lies down to rest on its side. The pale blue-green of Uranus suits its posture. It is the color of calm, of cool distance, of a planet far from the sun's warmth turning slowly in the cold. Whatever violence laid the planet over at the beginning, what remains is this soft-hued, quiet-faced world. Its air tinted the color of still water, drifting through the dark at the edge of everything, wearing the most restful color in the sun's family. A planet lying on its side carries its whole household with it, and the family around Uranus is one of the clearest expressions of the tilt. The planet is encircled by a system of narrow rings and attended by a company of moons, and because the planet is tipped nearly onto its side, this entire system is tipped along with it. The rings and moons do not circle a level equator around an upright world. They wheel around a planet lying down, in a plane turned nearly on end, sweeping up over one pole and down past the other as they orbit. The rings of Uranus are unlike the broad, luminous bands that make Saturn famous. They are narrow, dark, and faint, thin threads of shadowed material spaced around the planet, far more modest than Saturn's brilliant display. They are made of dark particles that reflect little light, which is part of why they went unseen for so long and had to be found by watching them blot out the light of a distant star. There are more than a dozen of these narrow rings known, slender and separate, tracing the tilted equator of the planet in a set of fine, faint circles. What holds these narrow rings in their tight, confined shapes is one of the quiet marvels of the system. Left to themselves, ring particles tend to spread out over time, their orbits gradually blurring into a broad, diffuse sheet. Yet the rings of Uranus stay narrow, their edges sharp. The explanation lies with small moons that orbit near the rings, sometimes called shepherd moons, for the way they tend their flock. Through the steady pull of their gravity, these little moons confine the ring particles, nudging back any that stray, keeping the narrow rings narrow. A ring held sharp by the patient tending of a nearby moon is a delicate arrangement, and Uranus maintains several of them. Beyond the rings orbit the moons themselves, a family of more than 24 known worlds, ranging from tiny bodies to substantial moons, hundreds or thousands of miles across. They circle the planet in the same tilted plane as the rings, riding the tipped equator, their orbits turned nearly vertical relative to the planet's path around the sun. To picture the system rightly is to imagine a set of circles standing almost on edge against the direction of the planet's travel, the moons rising and falling over the poles rather than sweeping around a level waste. It is a household arranged around a world that lies down, and it shares the world's posture completely. This shared tilt is what produces the target pattern we considered earlier, the nested circles the moon system traces when we see it face on from far away. It is also what makes the arrangement such strong evidence for the planet's history. As we have seen, the moons ride the tilted plane because, in the favored account, they formed from the debris of the ancient collision after the planet was knocked over, inheriting its new orientation. the tilted family is not merely a pretty arrangement. It is a record, written in orbits, of the event that laid the planet down and of the long, patient settling that followed. The moons closer to the planet feel its presence strongly, and the planet in turn shapes their paths and, in some cases, their surfaces. Tidal forces, the stretching pull a planet exerts on a nearby moon, can flex a moon's interior and warm it, especially where the moon's orbit brings it repeatedly nearer and farther from the world. This flexing heat, generated not by sunlight but by the working of gravity, may have shaped the histories of some of the inner moons, driving activity on worlds that would otherwise be frozen still. The family is not a set of inert stones. It is a system of worlds, bound to a planet and to one another, shaped by the forces that pass between them. The rings themselves repay a closer look, modest though they are. They differ from one another in width and in character, some as narrow as a few miles across, fine threads of dark material traced around the planet. The outermost of the main rings is the widest and most substantial, though even it is slender beside the bright expanse of Saturn's. The particles that make up these rings are dark, reflecting little light, more like fragments of charcoal than the bright ice of Saturn's bands. It is a subdued and understated ring system, fitting for so understated a world, easy to miss, and quietly lovely once found. The appearance of the whole system to a distant watcher changes slowly across the planet's long year. Because the rings and moons share the planet's tilt, we see them from a shifting angle as Uranus moves along its orbit, the system opening toward us and then closing again across the decades. A patient observer, watching across a lifetime, would see the tilted family turn slowly through its phases, from open target to closed line and back again, a gradual wheeling that marks the passage of the planet's seasons in the geometry of its rings. Seen whole, the tilted family gives the planet a particular kind of grace. Uranus is not a solitary world. It travels with a retinue, a set of dark rings, and a company of moons, all of them keeping faith with its tipped posture, all of them arranged around the sideways axis, the collision set in place. Where the planet leans, they lean. Where its equator points, they orbit. The whole system moves as one tilted unit through the dark, a single arrangement of planet, rings, and moons, all sharing the consequences of that one ancient blow. There is a companionship in that, of the quiet, astronomical kind. However the planet came to lie down, it does not lie down alone. It carries its moons and rings with it through the long cold, a tilted household moving together around the distant sun. And among those moons is one small world stranger than the rest, a moon that seems to wear its own history of upheaval on its broken surface. To that curious little world, and to its larger siblings, we turn now. 5 of the moons of Uranus stand out from the rest by their size, 5 substantial worlds that make up the major family of the planet. In order outward from the world they circle. They carry the names Miranda, Ariel, Umbriel, Titania, and Oberon. Their names set them apart from most moons in the Sun's family, which are drawn from ancient mythology. These are drawn instead from the plays of Shakespeare and the poetry that followed, a literary company of moons circling the tilted planet, named for characters of the stage rather than gods of old. The 2 largest, Titania and Oberon, orbit farthest out among the 5. They are worlds of ice and rock, cratered by the impacts of ages, marked here and there by long cracks and valleys where their surfaces have been pulled apart in the distant past. They are cold and old and quiet now, keeping their scars, turning slowly around the planet in the outer reaches of the major family. Umbriel, orbiting nearer, is a darker world, its surface dim and heavily cratered, one of the less reflective moons, holding on to the shadows. Ariel, nearer still, shows a brighter and somewhat younger-looking surface, crossed by valleys and marked by signs that it was, at some time in its past, reshaped by activity from within. Closer to the planet than these 5 major moons lies a busy inner region, crowded with far smaller bodies. A number of tiny moons orbit here, some of them tending the narrow rings, confining the dark ring particles with their gravity, as we saw earlier. This inner company is a delicate and tightly packed arrangement, the little moons and the fine rings sharing a small region close above the planet, all of them riding the same tilted plane as their larger siblings farther out. That such small bodies can shape the rings at all is a reminder of how gravity works patiently across a system, the least of the moons keeping the rings in order through nothing more than the steady pull they exert. The inner region of Uranus is a quiet machine of small parts, each holding its place, each contributing to the balance of the whole, a system within the system, easily overlooked beside the 5 great moons, but no less a part of the tilted household the planet carries through the dark. But the small moon that draws the most attention is the innermost of the 5, Miranda, and it is among the strangest small worlds anywhere in the Sun's family. Miranda is not large, a modest ball of ice and rock, and by its size alone one would expect a simple, uniform, heavily cratered surface, the ordinary face of a small frozen moon. Instead, Miranda shows a surface unlike almost any other, a patchwork of mismatched terrains, jammed against one another as though the moon had been assembled from ill-fitting pieces. On Miranda, smooth plains lie beside grooved and ridged provinces. Regions of one character end abruptly against regions of another, with sharp boundaries where wholly different kinds of terrain meet. There are systems of parallel ridges and troughs, great grooved ovals set into the surface, and enormous cliffs. Among those cliffs are some of the tallest known anywhere in the Sun's family, faces of ice and rock that plunge for miles, so high that an object dropped from the top would fall for a long time before reaching the bottom. For so small a moon to carry such enormous features is one of the quiet marvels of the Uranian system. How Miranda came to look this way is not fully settled, and it remains one of the small mysteries of the tilted world. One idea is that the moon was, at some point, broken apart by a collision, and then drew itself back together under its own gravity, its pieces reassembling imperfectly into the mismatched patchwork we see. Another idea is that heat generated within the moon by the tidal flexing of the planet's pull drove slow upheavals in its interior, pushing different materials to the surface at different places and times, and building the jumbled terrain from within, rather than from a shattering blow. It may be that both played a part, or that the truth is something not yet imagined. Miranda keeps its own counsel, as the planet does. It is worth holding the scale of these moons in mind, for they are worlds of real size, not mere specks. The largest of them are hundreds to something over 1,000 miles across, substantial bodies of ice and rock, each large enough to have pulled itself into a round shape under its own gravity. They are smaller than our own moon, and far smaller than the great moons of Jupiter and Saturn, but they are true worlds nonetheless, with surfaces and histories of their own. Ranged outward from the planet, they form an ordered sequence, each keeping its own distance, each circling the tilted equator in the shared plane of the family. Miranda, the smallest and innermost of the 5, is also the one that most rewards a closer look, precisely because its size makes its features so unexpected. A small moon should be a simple thing, long since cooled and quieted, its surface a plain record of ancient impacts. That Miranda instead shows such varied and dramatic terrain, such enormous cliffs and such mismatched provinces, suggests it had a more eventful history than its size alone would predict. Something worked upon this little world, whether from without or from within, and left it marked in a way that continues to puzzle those who study it. There is a question that hangs over these moons, as it hangs over the icy moons of the other giant planets, and it is a gentle and hopeful one. Some moons in the outer sun's family are thought to hide oceans of liquid water beneath their frozen shells, kept from freezing by the warmth of tidal flexing, sheltered seas held far below the ice. Whether any of the moons of Uranus conceal such hidden oceans is not known. Our single distant look was not enough to tell. But the possibility is real, and it lends the tilted family an added quiet interest. The chance that beneath one of these cold and cratered shells, a dark sea may be turning slowly in the depths, unseen. These 5 moons, and the smaller ones that accompany them, are the near household of Uranus, the worlds that share its tilt most closely and feel its presence most strongly. They record, in their orbits, the ancient event that tipped the planet, and they carry, on their surfaces, the marks of their own long and separate histories, of impacts and flexing and slow reshaping across an age. Miranda's broken face, Ariel's reworked valleys, Umbriel's darkened plains, the cratered calm of Titania and Oberon, each is a small world with its own story, bound to the tilted planet and to one another. To consider them is to be reminded that Uranus is not a single object but a system, a whole small world of worlds, turning together in the cold. The planet lies on its side, and its moons lie with it, each keeping the tilted plane, each carrying its own scars and quiet possibilities. They are the closest company the sideways world keeps, the nearest witnesses to its long rest, and they will go on circling it, faithfully, through a length of time that makes this night seem shorter than a single breath. For all that we have said about Uranus, it is worth pausing to remember how thin our direct knowledge of it truly is. Almost everything humanity has learned from close range about this planet comes from a single visit by a single spacecraft that did not stay. One probe, on a long journey outward through the Sun's family, swept past Uranus in a matter of hours, gathering what it could as it flew, and then continued on toward the far edge of everything, never to return. That brief encounter, together with patient watching through telescopes from afar, is the foundation of nearly all we know. Consider what that means. The tilt, the seasons, the rings and moons, the crooked magnetic field, the missing heat, the strange interior, all of it rests, in large part, on the data gathered during one fast passage and on careful observation from a great distance. No spacecraft has ever settled into orbit around Uranus. No probe has ever descended into its atmosphere. We have never lingered at this world, never watched it through a full turn of its seasons up close, never studied its moons at leisure. We met it once, briefly, in passing, and then we were carried onward by the same motion that brought us near. That single visit happened to arrive near one of the planet's solstices, and this timing shaped everything that followed. With a pole turned toward the sun and much of the planet locked in its long steady day or its long steady night, the atmosphere was in its quietest state. The spacecraft saw a smooth, near-featureless ball, a placid, pale disk with almost nothing to mark it, and sent home the impression of a bland and sleepy world. It was, in a sense, a portrait taken at the calmest possible moment, an accident of timing that fixed our picture of the planet as duller than it is. For a long while, that quiet portrait stood as the image of Uranus, the featureless world at the edge of the Sun's family. Only as the years passed, and telescopes improved, and the planet moved on toward livelier points in its long year, did the fuller picture emerge. Watchers caught Uranus with storms brightening in its atmosphere, with bands and clouds and a passing dark spot, a world more active and more interesting than the single flyby had suggested. The planet had not changed. Our view of it had simply been widened, corrected by patience, freed from the accident of a single well-timed calm. It is worth remembering, too, how far our one visitor had to travel to reach the planet at all. Uranus orbits at roughly 19 times the Earth's distance from the Sun, far out in the cold, where sunlight is thin and faint. To cross that gulf took the spacecraft years of steady flight, a long, patient journey outward through the Sun's family, before the planet finally grew from a point of light into a world. And when the machine at last arrived, its whole, close encounter lasted only hours, a brief pass through the system before the planet fell behind and the probe continued on into the dark. Yet in those few hours, the visitor gathered a treasure of knowledge. It measured the strange magnetic field and settled the planet's rotation and studied the atmosphere. It found new moons and new rings that had been unknown before, and it caught the only close portraits we have of the major moons, including the broken face of Miranda. Everything humanity has seen of Uranus from nearby was gathered in that single swift passage. It was a remarkable harvest for so brief a visit, and it remains, decades later, the foundation on which nearly all our close knowledge of the planet still rests. That single passage was possible only because the spacecraft was already crossing the outer Sun's family on a longer journey, and Uranus happened to lie along its path. The visit was not a mission to Uranus alone, but one stop on a grand outward tour, a chance to study a distant world in passing before continuing on toward the next. This is part of why our knowledge is so thin. We have never sent a craft to Uranus for its own sake, to stay and study it. We have only passed by once, on the way to somewhere farther out, and gathered what we could in the hours the planet was near. Everything learned since has come from watching the planet from afar, refining and extending that one brief encounter without ever renewing it up close. The planet has not been visited in the time it takes a person to grow from childhood into the middle of life, and it may not be visited again for many years yet. For a world so full of mystery, that single passing glance is a slender foundation indeed, and it is a measure of how much the planet still holds in reserve. There is a quiet humility in this, and it is worth holding on to. So much of what we confidently say about Uranus rests on one brief look, caught at an unrepresentative moment, and on the slow gathering of distant observations since. This does not mean our knowledge is wrong. The tilt is real, the missing heat is real, the strange field is real, all measured and confirmed. But it does mean our knowledge is incomplete, sketched from limited sight, with much of the fine details still guessed at rather than seen. We know the outline of the sideways world far better than we know its particulars. It is a strange thought that a planet so large, so full of mystery, so central to the story of how the Sun's family formed, should have been visited only once, and so briefly, in all of human history. The other worlds nearer the Sun have been circled by orbiters, touched by landers, studied for years at close range. Uranus has had a single fast passage, and nothing more. It remains, in a real sense, the least known of the major planets, the one we have met the least, holding most of its secrets still, out in the cold where few of our machines have ventured. And yet that very incompleteness is part of what makes the planet quietly compelling. Uranus is not a closed book, its story fully told. It is an open question, a world we have barely begun to know, still waiting to be properly met. The tilt that laid it down, the heat that fell silent, the field that leans so strangely, the moons that may hide seas, all of these remain not fully understood, held in reserve by a planet that has shown us only a single glance of itself. There is more to learn here than we have yet learned, and the planet is patient, and it is not going anywhere. So when we picture Uranus, it is worth holding both things together, gently. We know a great deal, enough to tell its story, enough to reason well about its past. And we know very little, enough only to sense how much remains hidden. The sideways world has given us one look, long ago. And from that single look, and the patient watching since, we have built the understanding we have. What waits beyond it, in the details we have never seen up close, is a matter for the future, and for a return we have not yet made. Because our one close look was so brief, and caught the planet at so quiet a moment, much about Uranus remains genuinely unknown, and it is worth naming these open questions plainly, for there is a calm pleasure in knowing exactly where our knowledge ends. The planet holds several mysteries still, each one a place where reasoning has carried us as far as it can, and where only a closer study could carry us further. We do not know, with certainty, exactly how and exactly when Uranus was tipped. We have the leading account of a great collision, and strong evidence for it in the arrangement of the moons and the coldness of the interior. But whether it took a single blow, or several, precisely when in the planet's early life it happened, and precisely how the event unfolded, remain matters of reasoning rather than direct sight. The broad answer is in hand. The particulars are not. We do not fully understand why so little heat escapes from the planet. We know that Uranus radiates almost exactly the sunlight it absorbs, and barely more, while its twin Neptune glows with far greater inner warmth. We have two good ideas: that the collision either expelled the planet's heat or sealed it away beneath still, unmixing layers. But we cannot yet say which is true, or whether both play a part, and telling them apart would require measuring the interior in ways a single distant flyby could never manage. The missing heat is measured. Its cause is still reasoned rather than known. We do not know why the magnetic field leans so steeply and sits so far off center. We have the idea that it arises in a thin shell of conductive fluid, rather than a central core, which could account for its irregularity. But the true structure of the planet's interior and the exact way it generates its crooked field remain to be mapped. To understand the field properly would mean watching it swing through many complete rotations from nearby, gathering the kind of detailed measurement no passing glance can provide. We do not know whether any of the moons hide oceans of liquid water beneath their icy shells, as moons of the other giant planets are thought to do. The possibility is real, and it lends the tilted family a gentle interest, but our single distant look was not enough to settle it. Nor do we fully understand Miranda's broken patchwork surface, whether it was shattered and regathered or reshaped from within, or what its jumbled terrain is truly telling us about the history of the whole system. These small worlds keep their secrets, much as the planet keeps its own. The natural answer to all of these questions is a return, and the case for going back is strong. Space agencies have identified a dedicated mission to Uranus as a high priority for the future, a spacecraft that would not merely pass by, but settle into a long stay, circling the planet across years rather than crossing its path in hours. Such a mission might carry a probe to drop into the atmosphere, sampling the air directly as it fell, and might study the moons and rings up close, patiently, in a way no single flyby ever could. An orbiter at Uranus could measure the interior from many angles, testing whether the heat is truly gone or merely trapped. It could watch the crooked magnetic field swing through complete rotations, mapping its strange structure in detail. It could examine the moons closely, searching for the signs of hidden oceans, studying Miranda's broken face from nearby. And it could, for the first time, test the story of the ancient collision against detailed evidence rather than distant reasoning, reading the planet's past in the fine particulars we have never yet been close enough to see. None of this would be easy, and the difficulty is part of why we have not yet gone back. Uranus lies far out in the cold, and reaching it takes many years of travel, a long, slow crossing of the wide gulf between the inner worlds and the outer dark. So far from the sun, sunlight is too faint to power a spacecraft easily, and a mission must carry its own long-lasting source of energy to work at such a distance. A journey to Uranus is a commitment measured in decades, from the launching of the craft to the gathering of its final data, longer than many careers. And yet the reward would be great, which is why the case keeps being made. A single well-equipped orbiter, settled at Uranus for years, could answer questions that have stood open since the one brief flyby, testing the story of the ancient collision against close and patient measurement. It would be a long investment in learning, a machine sent across an age of travel to study a world that has kept its secrets through a far longer age still. A probe dropped into the planet's atmosphere would answer a particular set of questions that no distant study can reach. As it fell, it could measure the true makeup of the air directly, sampling the gases in their proper proportions, reading the temperature and pressure at each level as it descended. It could sense the winds by the way it was carried along and feel the structure of the cloud layers as it passed through them. Such a descent would last only a short while before the probe was lost to the thickening fluid below, but in that brief fall, it would gather knowledge of the planet's atmosphere far beyond anything gathered from outside. Paired with an orbiter watching from above, such a probe could tie the planet's visible face to its hidden interior, connecting the clouds we see to the structure far below. Together they would begin to read the world whole and to test at last the story of the ancient blow against the evidence of the planet itself. The planet has waited. A mission would simply be our part of the waiting, the slow work of finally going out to meet it. Until such a return is made, the planet keeps its own counsel. It holds the details of its accident, the reason its furnace fell quiet, the structure of its interior, the possibility of seas within its moons, all in reserve, out in the cold, where we have visited only once. There is no impatience in it. The planet has waited an age already, tipped on its side, turning slowly, and it can wait a while longer for us to come back and learn what it has not yet shown. The questions are not troubling ones. They are simply the honest, open edges of what remains to be known about the strangest of the major worlds. So we come, at the end of this long night, back to the simple fact we began with. Uranus lies on its side. Alone among the major planets, it does not stand upright as it circles the sun, but rests nearly flat, tipped almost a full right angle, rolling through its long, slow year, with its poles pointing out toward the side. Everything we have followed tonight flows from that one fact, from the 42-year days to the tilted family of moons to the quiet cold of its interior. We have gathered the leading answer to why it lies this way. Long ago, at the very beginning of the Sun's family, when the space around the young planet was crowded and unsettled, something very large is thought to have struck Uranus a glancing blow, or perhaps several, and turned the whole world onto its side. From the debris of that collision, the tidy family of moons may have formed, inheriting the planet's new tilted plane. And in the same event, the planet's inner warmth may have been expelled or sealed away, leaving it the coldest world in the Sun's family. One ancient blow, tying together the tilt, the moons, and the missing heat into a single quiet history. We have also held the honest uncertainty gently. The collision is the leading explanation, not a proven one. Quieter possibilities remain: a large moon since lost, a resonance swept up in the migration of the giant worlds, patient gravity doing over an age what a blow might do in a moment. And with only a single brief visit on record, much about the planet stays genuinely unknown, held in reserve until we return. The outline of the story is clear. The finest details are still the planet's own. But whatever laid Uranus down, the thing worth carrying away from this night is how the planet has borne it. The collision, if there was a collision, was brief, a single event at the dawn of everything. What has followed is an almost endless calm. Through the long forming of the other worlds, through the settling of their orbits, through an age of time beyond any counting, Uranus has simply gone on turning quietly on its side, in no hurry to right itself, keeping its moons close, drifting through the cold. The violence is entirely in the past. What remains is a pale blue-green world at rest, undisturbed, patient beyond imagining. There is a kind of peace in that, if we let it settle over us. A whole world was knocked over at the beginning of time, and rather than struggling against it, the planet simply accepted its new posture and went on. It did not need to stand back up. It found a way to keep turning as it was, laid gently on its side, and it has done so, without complaint, for longer than the mind can hold. Its seasons stretched to match its tilt. Its moons gathered themselves around its new plane. Its whole life rearranged itself, calmly, around a single old accident, and made of it something settled and quiet and enduring. Perhaps that is the gentlest thing the planet has to offer, on a night meant for rest. Not every disturbance must be undone. Not every tilt must be righted. Uranus was knocked from its upright course at the very beginning, and instead of struggling to stand again, it simply carried on, turning as it was, and made a long and peaceful life out of a new and unchosen posture. The collision did not define the planet. What defined it was the calm that came after, the endless quiet turning, the slow settling of its moons, the patient keeping of a tilted course through the dark. There is comfort in a world that was overturned and found its peace anyway. Whatever leans in your own life tonight, whatever sits at an unexpected angle, the planet is a quiet reminder that things knocked sideways can go on turning, steadily and well, for a long time still. The sideways world does not ask to be set right. It only keeps drifting, cold and pale and calm, through the long dark at the edge of everything, at rest with what it is. So let the sideways world drift now at the edge of your thoughts, as it drifts at the edge of the sun's family. Let it turn there, pale and cold and unhurried, its poles trading places between decades of light and decades of dark, its faint rings and its literary moons wheeling around its tilted equator, its story mostly told, and partly still, its own. Whatever struck it did so long, long ago, and the planet has been resting ever since. There is nothing here that needs your worry, and nothing that needs your watching. The planet will keep turning whether or not anyone observes it, as it has through all the long dark before this night and will through all the long dark after. Let your breathing slow. Let your shoulders soften and settle. Let your own thoughts tip gently, like the planet, toward rest, leaning softly away from the cares of the day. The sideways world is at peace out there in the cold, and you may be at peace here. Sleep well, and good night.